Welcome!
Welcome!
Welcome to the world of ballistics.
Come and journey along with us as we explore muzzle velocity, projectile motion, and much, much more with the help of our good friend, the ballistic pendulum.
For our exploratory lab, we study about ballistics. The definition of ballistics is the study of the motion and impact of objects launched or thrown at some initial velocity with subsequent motion gravitational acceleration, which is called projectile motion. Ballistics is used to help design and accelerating projectiles to achieve a desired performance for those who deals with the launching, flight, behavior, and effects of projectiles for things like bullets, gravity, bomb, and rockets. The two items of interest in ballistics are the initial speed of the projectile, which is the muzzle velocity, and the maximum horizontal distance traveled before impact with the horizontal surface.
So, two practical applications of ballistics in physics are one, when looking at forensics with gunshots. A lot of times they use the forensics on the gunshot to close cases quicker. And another practical application of the ballistics in physics is in older times when they would shoot off cannons in battle. You would need to understand the trajectory and the ballistics in order to be able to inflict the most possible damage on the other army. So.
Now let's talk about our experimental apparatus. This is the 3-speed projectile launcher portion of our apparatus. As you can see, there's a short range, medium range, and long range setting. The force is applied by a spring. This shows the projectile launcher mounted on the ballistic platform. Here we see again the launcher along with the ballistic pendulum, which is at top left. The pendulum can be used to fire projectiles into it and get an angle reading. Here we have our good friend Sung, who is going to demonstrate for us what that looks like. Sung has a projectile and a plunger to help her set the launcher. Once the launcher is set, the ballistic pendulum is lowered and the angle is set to 0 to give us an accurate angle reading. For this first experiment, we have the short range. This appears to be at about 15 degrees. Next, the medium range setting is used. Sung fires, and it looks to be a little over 30 degrees. Now we have finally the long range setting. The reading here looks to be 46 degrees. Showing the 3 launches again, short, medium, and long range, we see that the results are what we would expect. As the force increases, so does the angle. As Durand will be demonstrating for us, here we have a new setup of our experimental apparatus. The launcher has been moved from the lower portion of the base to the upper portion, and the photogate timer has been added to it. The photogate timer is used to measure the velocity of the projectile just as it leaves the launcher. This is the muzzle velocity. Here we see in slow motion. Through our various trials with the plastic ball at medium range and the metal ball at long range, we found the velocities to be 4.85 meters per second and 4.870 meters per second, respectively. The next portion of our experiment is range as a function of launch angle. This explores the effect that the angle of the launcher has on the horizontal distance that the projectile travels. To do this, we must accurately determine the point at which the projectile makes contact with the horizontal surface. Sung was responsible of making the preliminary determination of the point of contact. Although it was not in the methods, we found the use of the plunger extremely helpful. Sung proved to be an expert in the use of this research tool. When the point of contact is determined, you'll see Durand placing a white piece of paper at that point and taping it down. Test it. Looks just right. Next, Durand places carbon paper over the printer paper. Five launches were made for every 10 degrees, starting with a 10-degree angle and ending with an 80-degree angle. A little slow-mo action for your enjoyment. As Durand takes up the carbon paper, we will see the points at which the projectiles hit. The next step is to measure from the point on the floor directly below the release point, which we determined earlier, to the closest edge of the white printer paper. Now we see Sung using the ruler to measure the distance from the edge of the paper to each point. The data from our experiment yielded the following results. This spreadsheet from our data analysis lists all launch angles 0 through 90 and the theoretical time and range calculated with formulas in Excel. The far right column is our experimental data results. This graph represents range in meters plotted versus launch angle in degrees. The blue curve is the expected theoretical result, and the data points are our actual results. The close alignment of our data with the theoretical shows that our actual results aligned very well with the theory and equations outlined in our lab. For the final part of our analysis, we compared our photo gate muzzle velocity result with a calculated muzzle velocity using values obtained from experimentation with the ballistic pendulum. There is both an equation that was approximate and one that was more exact. The low percent difference for these values again shows that our data aligns very well with the theory.
In our ballistics exploratory lab, we have learned how to to perform different types of measurements to relate projectile motion to launch angle, muzzle velocity, and gravitational acceleration. We have related projectile motion to launch angle by firing the plastic ball from the medium range position with different launch angles. Muzzle velocity was found by using the photo gate timer. We timed the speed of the different types of balls traveling 10 centimeters from the medium range position. Lastly, we have found the gravitational acceleration by using the ballistic pendulum to determine the speed by indirect means using the principle of conservation of momentum and conservation of energy.
It's beginning to look a lot like Christmas everywhere you go. Take a look at the 5 and 10. It's glistening once again with candy canes and silver lanes that glow. It's beginning to look a lot like Christmas. Toys in every store, but the prettiest sight to see is the holly that will be on your own front door. A pair of hop-along boots and a pistol that shoots is the wish of Barney and Ben. Dolls that'll talk and will go for a walk is the hope of Janice and Jen. And Mom and Dad can hardly wait for school to start again. It's beginning to look a lot like Christmas everywhere you go. There's a tree in the Grand Hotel, one in the park as well. It's the sturdy kind that doesn't mind the snow. It's beginning to look a lot like Christmas. Soon the bells will start, and the thing that'll make them ring is the carol that you sing right within your